harmonic motion. Okay, so this is angular velocity. Velocity is that's our omega, right? And then this is our friend, the period, right? So for example, if the period is 1, then your angular velocity is 2 pi radians per second. Right? You go around once a second. Okay. This is the acceleration. So if you have an oscillator like this, and here's our equilibrium position. If we're here, regardless of which way we're moving, we could be moving to the right. Maybe our equilibrium or our amplitude is here, right? And then it goes to here, right? Okay, this gives us our acceleration. Okay, and it's minus omega squared times x. So you got to find omega maybe with this, right? And then it's the opposite of that. So understand that if we have a positive x, right? Remember that our acceleration is that way. If we're here, let's say we're here, right? Our acceleration is this way. And the reason for that is a formula that's not in the data packet, is that springs always exert a force that try to put you back to x equals 0. So here's 0, here's minus the amplitude plus the amplitude, right? This spring is always trying to make you go back to this spot, okay? There it is, right? So there's our acceleration. This is the associated, wow, well, they really did a number. These guys are with each other. They go together. So if this is our position, so this is our amplitude, right? This is our omega that we just talked about. That's time, right? Okay. This one goes with this guy. So that's your equation for x. This is your equation for y. Now, at this point in your life, you should realize that this is the derivative of this. If you do the chain rule, you take the omega out front, and then the derivative of the outside function of sine is cosine, right? Okay, so these guys go together. These guys also go together. Okay, they group this way, right? Okay, so if this, by the way, if it is x, the derivative of this is, well, it's a chain rule, so the omega comes outside, derivative of cosine is negative sine, right? There it is, right? So these guys go together. Remember, this is this w x naught, that's your maximum velocity. That's your maximum velocity is omega x naught, right? And then you can just use this. Make sure you are in radians when you do this, right? This is, if you know the position of something, right? So maybe it's here, right? This is where you are now, your position. This is the amplitude, right? And then this is our omega as in this, right? Okay, and this will give you the speed, but if you only give me a position, I won't know where I am, okay? And then this is our total energy of our system, which is interesting, right? We got to have the mass there, and then notice that this is really just 1/2. Omega x naught is the maximum velocity, so really it's 1/2 m times the maximum velocity squared is what it is, right? Okay. And then if we do some maths here, right? Omega is 2 pi over t, right? And then if we plug this in for t, well, 2 pi divided by 2 pi times the square root of m over k is just square root of k over m, right? So omega secretly is square root of k over m, right? And so also if you look at this, right, if I put that in there, 1/2 m omega squared x naught, right? 1/2 m omega squared is, well, it's k over m squared times omega squared. Oh, whoops, times x naught. Okay. If you look at this, well, look at, if we square that, that becomes k over m, right? And the masses cancel, and it's also 1/2 kx naught squared, right? So this is our total energy. And then this is our energy at x. So if we're at some position where this will be our kinetic energy, kinetic. Okay. Now the potential energy, you have to read between the lines, right? Potential would be total minus kinetic. Okay. So if they ask you for the potential energy, which maybe they won't, I don't know. Okay, there it is. And then this is for a pendulum. So if you've got a pendulum like this, and it swings back and forth. This is the length of the pendulum. And for small amplitudes, it does not depend on anything except the length and how strong gravity is. And you can use this, by the way, you can use this formula. And if you very accurately measure the period of a pendulum, you can show that the period of the pendulum is slightly different at Timberline Lodge than it is in Portland, and therefore deduce the change in the G. But you have to be real careful and do a lot of trials and et cetera, et cetera. It's interesting. But that's for a pendulum. Alrighty.